Okay, hello, welcome back. So now we are still in the topic of angular velocity. We have so far seen how we can relate angular velocity to the rate of change of Euler angles a couple of videos ago. How we can relate angular velocities to the rate of change of rotation matrix. Now is the time to see how we can relate angular velocity to the rate of change of variables that define this axis angle representation. So to do that, just maybe as a reminder, imagine I have this, that's very long, big X, Y, and Z, which is my original frame, and a frame that is rotated has become this X, Y, and Z. I can do a prime because of the requests. Let me try another color, orange. And with axis angle, we represent this rotation as a rotation about some axis defined by unit vector A and some amount of rotation phi. And this is the axis angle representation. So at this instant that the frame has already rotated some angle phi about some axis A, the frame is continuing to rotating, so it has some angular velocity. So its angular velocity, let me do a bit of writing. The angular velocity of the frame that we are considering is, as before, omega x in I plus omega y in j plus omega z in k. So these are the components of angular velocity in the body fixed frame along the little ijk. So at this instant, because the body continues to rotate, it means that possibly the axis is also changing through space, and the angle that goes with it also changes. So we have both A and phi changing with time as the frame continues to rotating. So I tried to find the proof, I couldn't. What you can do, maybe ask Euler, I don't know. Omega can be written as phi dot times A plus sine of phi A dot plus 1 minus cosine of phi A cross A dot. And this is the equation, accepted without proof. So it is useful when this equation on its own is useful when you know, for instance, how your axis, so let me maybe draw it. Consider I don't know, a random body. It's this point is fixed. I have, I don't know, let's pretend that I have a disk that is rotating about this axis. So I hope you can see it. The body is rotating about this, the disk is rotating about the axis, and the axis itself is rotating somehow in the space, and you know it. You know how. So in this case, you can fairly easily find your A and A dot in any at any time, and you know the rate of change of this phi. So for instance, there is a motor running at a speed, or somehow you have measured it. You can then find the rate or the angular velocity of the body, this disk, using this equation. Well, let me add another thing. Do I need to add another thing? No, not for now. So it is useful if you know your rotation your axis of rotation and the angle of rotation and how they're changing. You can get the angular velocity of the body. The other way around is a little more involved. Well, this one was probably more involved because I couldn't find the proof. Probably the proof is quite long. I don't know. But the other way around is not too simple either. So let's go the other way around. We know omega. I don't know. I have some kind of sensors placed in my system to measure it. We want to know phi dot and a dot. So phi dot is easy. To get phi dot, what I can do is take this equation and take the dot product of that with a. So it's going to be phi dot a plus sine of phi a dot a plus 1 minus cosine of phi a cross a dot a. So many dots. This is a dot. So something to note here, this is identity 1, because a, remember, a is a unit vector. A dot, because a is a unit vector, a dot is actually always perpendicular to a. So this is 0. And this one is by definition perpendicular to a and also a dot. So actually we are top here. All three, oh, that's not 3. All 3 are perpendicular vector. So all 3 terms in this are perpendicular to each other. So this one also 0. So what I have is actually just phi dot. Let me write it the other way. So from here, phi dot is omega dot a. So rather compact, useful. So if I know the vector of my angular velocity, I can find the projection of that along the axis of rotation. That gives me the rate of rotation about that axis. And I think it is, I'm not too sure, but my senses say that this is true for any arbitrary axis. If you have your vector of angular momentum and you want to know what is the equivalent rotation about any arbitrary axis, you just make a dot product of omega to that axis. That would be your rate of rotation about that particular axis. So quite useful. To get so that is phi dot. To get the a dot, the derivation is in the textbook. It's going to be rather long. What I do is actually skip everything and give you the final answer. A dot is minus half times a cross omega plus cotangent of phi over 2 or 1 over tangent, whatever you want to write, a cross omega. And this is how your vector A, the unit vector A, is changing in a space. Again, if you know your current A and your vector omega, you can get how A is changing. It is useful, but actually it's not this particular form of A dot is not as useful as we hope. So I know omega I can write it as a function of ijk or its component along the little ijk. And I can write my A also as some component along xy, little xyz. So I can have omega equals omega xi, omega y, j, why am I putting commas, plus omega z k. I can also write A as axi plus a yj plus a zk. But note that this a dot that I have here is the total change of the vector A. So a dot is not a dot xi plus a dot yj plus a dot zk. So these components, remember when we were talking about in the kinematics chapter, this is a dot relative, what we call relative. So the observer, when sitting on the rotating frame, how they see this vector is changing. So this is the relative measurement of that. And to have a good comparison between current omegas and a x, a y, a z, we would like to know these a dot x, a dot y, a dot z, instead of the full change of matrix. And if you remember, for instance, when you have velocity or anything, a dot is actually a dot relative plus omega times or cross a. You had this equation in a more familiar way of velocities, for instance. This is the one I want to find. So what I can do is a dot relative. Oh, it's not here. A dot relative is a dot minus omega plus a, or this one I can write it as a dot plus a cross omega. If I flip the order, the sign also flips. And I know a dot from the top equation. Actually, there is some a cross omega in the first term. So adding this is going to give me a dot r, a dot r, which is a dot x I plus a dot y j plus a dot z k equals 1/2 of. So this half of this there cancels out with that one. So only a positive half will remain. I'll take out the half. I have a cross omega and just to keep the signs correct, minus cotangent of phi over 2 a cross omega. So this is kind of useful, and we'll see more useful version of this, kind of similar but slightly different version of this. So imagine you have a sensor in your the angular velocity sensor, and there is a good sensor for that. It's called gyro in the IMUs. You can measure this omega xyz and start from just some reference angle and start integrating this essentially differential equation to find your ax, ay, and az, and that very easily defines your final orientation. It becomes a lot more clear and nicely represented when we consider the Euler parameters, or Euler parameters. I stop here in the next video. So, all right, this is how you can relate angular velocities to the rate of changes of axis and angle of rotation. And the last one that remains is Euler parameters. So that would be next video. All right, until then.